So this example asks us to find a basis for the span of the 4 vectors here. So let me actually just call up the definition of a basis again. For something to be a basis for the span of these vectors, they have to be linearly independent. So for whatever, we don't know the dimension of the span of this guy, but whatever it is, that many vectors, they have to be linearly independent, and the span of those vectors has to equal to the span of the 4 vectors that we have here. Let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12. Okay, there actually are several ways to do this, but let me actually just show you the simple one first. So, what we are gonna do is that we will put these vectors into the tentative basis, and then we'll keep adding more vectors, keeping the vectors in our list linearly independent until we have enough vectors that have that, so that the span of those vectors is the span of the original space. So let's start off with the first one, 1, 2, 3. Well, if I have just one vector, then obviously this guy is linearly independent of itself. Well, there's nothing to be dependent against. So this guy automatically is linearly independent. Now let's see if I have 2 of them. What's gonna happen if I have 1, 2, 3, and 4, 5, 6? So I need to check if these 2 guys are linearly independent. So what I always do, I solve this system, or I solve for this vector equation, y plus 4, 5, y times 4, 5, 6 equals 0, 0, 0. And then the augmented matrix for this guy is gonna be 1, 2, 3, 4, 5, 6, and then all 0. I do the row operation, and that's gonna give me 1, 0, 0, 1, 0, 0, 0, 0, 0. Okay, so these 2 guys, they are linearly independent, so I put them into my tentative list of bases 4, 5, 6. Okay. Let's move on. The next one that I have is gonna be 7, 8, 9. So let's see if I have these 2 guys. Okay. If I have these 2 guys and 7, 8, 9, would they still be linearly independent? So let me actually just go ahead and write the augmented matrix. That's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then my right hand side is gonna be all 0. Now then, if I were to row reduce this guy, that's gonna give me 1, 1, 0, 0, 0, 0, negative 1 here and 2 here. So that means, wait a minute, I have too many lines. So that means the solution for this system is my x3 is a free variable, and then my x1 will just be equal to x3, and my x2 will just be negative x3, negative 2x3. So that means 0 is not the only solution here. So these 3 guys, they are not linearly independent. In other words, 7, 8, 9 is linearly dependent of the first 2. So that means 7, 8, 9 should not be put into my basis list. So I skip them. Now let me move on to the next one. How about, okay, one thing before I forget. One thing I want to note is that the span of 1, 2, 3, and 4, 5, 6. Let me actually write that down. The span of 1, 2, 3, and 4, 5, 6 is going to be the same as the span of the 3 vectors altogether. I'll just have to paste again. Okay, and then 7, 8, 9. Okay. So the span of just the first two is actually enough to cover the first two and then the 7, 8, 9, and that's because this vector 7, 8, 9 is linearly dependent of, it's a linear combination of the first two. Okay, so I should not put in 7, 8, 9. How about the last one, 10, 11, 12? So let's see. So I check if 10, 11, 12 is linearly independent. It's linearly it's linearly independent of the first two. And then 10, 11, 12. So again, I write the augmented matrix. For this one, it's going to be 1, 2, 3, 4, 5, 6, and then 10, 11, 12, and then all 0. Once I do the Gaussian operation, the row reduced form, that's going to be 1, 1, 0, 0, 0, 0, and then negative 2, 3, 0, 0, 0, 0. So the solution for this guy is going to be negative, it's going to be x3, it's going to be 2x3, 2x3, negative 3x3, and then x3. So 0 is not the only solution, so I knew that this guy is, the last guy is linearly dependent of the first two, so I should not put them into the basis. And I would also knew that the span of the first two is actually gonna be enough to cover the span of these 4 vectors altogether. So 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. So that means just the first two vectors, 1, 2, 3, and 4, 5, 6, is actually already the basis for this vector space, for the span of these 4 vectors here. So this 2 guy and this 2 guy. Let me actually also note that the basis is actually not unique. So if you try to put in some vectors into your basis first, you'll get a different answer for this one.